Hello everyone again, and we are back with Professor Maguid Hassan. I know we have another minute to go. We have another minute to go. Professor Maguid is going to talk about cultural heritage preservation using smart structural health monitoring. He will have about 30 minutes. He will have about 30 minutes to talk. Then we will have about 10 minutes discussion or something like that. And I would like to welcome Professor Maguid. Professor Maguid is the Dean of the College of Engineering at the British University in Egypt. And as I defined him before, he is my second older brother with Dr. Sharif Murad. Dr. Maguid, you can start now if you like.
Thank you, Professor Youssef. And first, I'd like to thank you for inviting me to participate in this workshop, which is a good experience to be engaged with other colleagues across the world. The title of my presentation is Cultural Heritage Preservation Using Smart Structural Health Monitoring. Let me just give a brief about what this is going to be. This is basically some work that we've done by using or developing an abstract shape identifier for structural systems. And what I'm trying to propose in here is to explore the possibility of extending this approach or this concept to be used in the preservation of cultural heritage. So basically, we'll start by giving a brief about which structures are we referring to when we're talking about cultural heritage. And then a very brief about structural health monitoring, which I believe everybody is aware of. And then we'll define the objective. What is exactly are we trying to do by introducing these concepts. Then I will spend some time explaining and giving a brief about what we have developed, which is the smart pattern identifier. And it's smart in the sense that it's based on top of smart technology, whether that is artificial neural networks or fuzzy inference systems. And we've used both successfully in a range of structural systems, ranging from 3 degrees of freedom frames to 20 degrees of freedom frames. And then I'm going to discuss briefly again the issue of reliability of such heuristic-based approaches. I mean, this is not an analytical model, and it does not relate and rely on analytical modeling in a sense, but it's purely heuristic. And this actually would raise the issue of maybe generalization of such an approach and the reliability of these systems. So I'm going to present a reliability assessment framework that was developed for such systems in order to ensure that they satisfy at least a minimum acceptable level of reliability. And then I'm going to present what we envision to be a model to monitor cultural heritage structures. So cultural heritage, by definition, our colleagues in architecture and maybe archaeologists would define such structures as monuments or with cultural value that would document achievements of previous civilizations and the history of humanity in general. And such invaluable structures should be maintained and preserved for future generations as long as possible. And of course, they are characterized by unconventional structural systems, such as monuments and historic buildings, similar to what we've seen in the first presentation by Professor Sharif regarding Fatima Khatun building. So these are examples of such structures, and you'll see that basically I'm concentrating on a certain type of structure, which is a cantilever-like structure. So I'm referring to mosque minarets, obelisks, church towers, that sort of structure. So what we see here is Sharkasi Mosque, which both pictures actually are the minaret of that mosque, and the right-hand side is what our colleagues in architecture would call it as the top pavilion of this minaret, and actually it has been damaged and they are split, and as far as I know, they are not placed at the same location at this point. So both pictures actually represent a single minaret that's now split into two parts. This is another example of such structures, and this is Sultan Barqu in the 1800s and Qarqamas Mosque in the 1800s also, and both of them actually are missing the top onion-shaped part of the minaret due to damage over the years. Again, I mean, our pharaonic heritage would have, let's say, similar cantilever-like structures. They might not be constructed with the same materials, or actually follow the same structural system, but they have the same characteristic as being supported or fixed at base and free at the end. And these could be temple columns or obelisks, which belong to the category that we're referring to here. So when we talk about structural health monitoring, it's an important tool now. It's being introduced in all new structures that have certain characteristics, in the sense that they, for example, high-rise buildings and long-span bridges, and such tools would provide some level of continuous monitoring of these structures to ensure the healthy performance throughout their years of service or lifetime. In addition, in some regions where we have excessive or extreme earthwork activity, these might be integral components of structural control systems or smart control systems. So as an example, we have Burj Khalifa, which is the highest, as far as I know, until this point in time, the highest high-rise building in the world. I guess this will be overtaken by another building, maybe in Saudi Arabia or something. Skytree in Japan, Akashi Kaikyu Bridge in Japan, which is the, I guess, longest span cable suspension bridge, and Jumen Bridge in China. So all of these structures are now equipped with some level of structural health monitoring mechanisms in order to ensure their healthy performance throughout their lifetime. So when we say smart structural monitoring, smart structural monitoring is basically underpinned by smart technologies such as fuzzy logic, neural networks, genetic algorithms, or combinations of some or all of these. In addition, they employ smart sensors, and now smart sensors are developed using MEMS, which is micro electromechanical systems. And MEMS now allows the ability to develop sensors that are miniatured in size and have some level of processing abilities on the sensor itself. Because when we reach the size of a problem, let's say the Burj Khalifa problem, and the amount of sensors that has to be introduced into such a building, there is a problem regarding data processing. And if this is will be done centrally, this is going to be a huge problem. So some of this data processing is being done locally at the sensors, and then instead of sending raw data, much advanced and usable data is being sent to central processing units. And smart structural health monitoring will be able to handle vague and uncertain information. And as we've seen again in the first presentation, there's a lot of uncertainty regarding first structural modeling and again material characterization for such old structures, and that's again due to the absence of accurate structural models. So now we introduce the type of structure that we're aiming to monitor and the method that we are proposing to use. So the objective would be to develop a smart structural health monitoring technique to continuously monitor such structures, sound alarms in case of unacceptable deformed shape. And that's maybe I'm going to stress that in a little bit later on to introduce the concept of shape identification or monitoring. And to take into consideration various sources of uncertainty, of course, and should operate within an acceptable level of reliability. So this is what we envision, that this is what we're looking for to develop. If we have an obelisk, we would be able to, let's say, to attach sensors across or along the height of this obelisk. And these sensors would send data to and information to maybe two processors or two systems, as we see in here. We have actually two cycles integrated within this vision. The first one is a processor that would take the data of the pattern identifier or the smart structure health monitoring mechanism and calculate its reliability based on a set of failure modes or limit states, and improve the design of this system until we reach an acceptable design that would render an acceptable level of reliability. Once this is done, the operation cycle, which is this cycle, this is the operation cycle, you would have data coming through the smart health monitoring mechanism, which would sound alarms or present recommendations. So this is what we envision that this is going to be developed and produced in that sense. So now I'm going to spend some time presenting the concept of pattern identification, and we refer to it usually as abstract pattern or shape identification. This is a mechanism that was developed as an integral component within a smart controller for structural systems. And the concept is based that it identifies the abstract shape of a structure real time during, let's say, an earthquake event, and sends this shape to a controller that can actually introduce signals to a set of dampers. And we usually in our proposals, we're using MR dampers, which is magnetorheological dampers, which again include some smart materials as the fluid inside these dampers. And if the, based on the deformed shape, signals will go to specific dampers to be activated, and this would reduce the perform, or actually the vibration or the damage that would actually take place for the system. So this is a model for this pattern identifier. So we have earthquake excitation through the ground. This is a 3 degree of freedom system. Time history, or actually the displacements of each floor, goes through the pattern identifier, which will come up with the shape of, this is an abstract form or abstract deformed shape of the structure. Now, the main concepts of such a system comes from a comparison between a structure and maybe a human body, and that's what we refer to as a smart structure or an autonomous structure. So the human body has three main components, which is the brain, which we can refer to it as a processing unit, muscles, and several senses. And if we try to model a structural system that has the same set of components, so we would provide some sort of a computing or processor unit, which would act as a brain, a set of sensors that would detect movements or any characteristics that we're looking for, and a set of actuators, which in this case are MR dampers located at each level. And this autonomous structure or smart structure would behave similarly when it's under the effect of an excitation that was not really taken care of during the design process, which is, let's say, an extreme earthquake that was not really considered. So the sensors would identify through the first processor, would identify the abstract shape of this structure. This information will be sent to the another part of the processor, which is again part of the brain as we refer to it, which would send signals to the actuators, and it will fire maybe some or all of these dampers. And the MR dampers basically receive voltage, and this voltage change the viscosity of the fluid within these MR dampers, which would change the characteristics and the response to vibration. This would affect the vibration of the building itself. So since it's an abstract shape identifier, we're not really interested in the actual location or the actual displacement of each level. We're looking at relative displacements and whether these displacements were, let's say, zero, negative, or positive. And if we consider all potential combinations of the three levels, we get, in this case, we get about 27 combinations that looks, some of them would look like this. So these are the potential positions for this 3-degree freedom system. And if the pattern identifier can identify which one of these is actually the actual deformed shape of the structure at any point in time during an event, this could be taken into consideration through the control system if we're doing control. If we're only doing structural health monitoring, so if I'm actually can identify the shape and which one of these, maybe I can send a signal or a remark or an alarm or propose something which could be done by the smart structural health monitoring system. We used actually two smart technologies to develop these pattern identifiers: artificial neural networks and fuzzy inference systems. So this is the first model, which is the artificial neural network model. It has an input layer, and the input layer is basically the inputs coming from the 3 degrees, which is the displacement of each level. And then 2 hidden layers. One has 3 neurons and the other one has 9 neurons. And then there's an output layer, which has a single neuron, which conducts linear combination of all neurons of the previous layer. And each layer has, each neuron has its own activation function, of course. And for the basic design of neural networks, we have actually synaptic weights for each neuron. And these are the ones that are being changed during the training procedure. So this is the training scheme or training cycle for the artificial neural networks. We have earthquake records introduced to the structure, a structural model for the building. We conduct analysis, get time history. We have developed a spreadsheet model for the pattern classifications based on the time history, which represent the target pattern classifications. We present the time history to the neural network, compare the two, and then go through the training process. This is the neural network during operation. So you would actually real time, you have earthquake, neural network in operation, and this shape is being sent continuously to, let's say, a controller or another processor that might actually take decisions or make recommendations based on that. In multi-degree freedom system, which is actually, we reached 20 degrees of freedom for these neural networks, and you have maybe to consider, of course, you have a lot of combinations of these deformations. However, there's only few practical combinations that can take place. And in these high-rise buildings and with higher degree of freedom, you might have several degrees of freedom, actually several levels moving together as a block. And that's the type of neural network model that was used in this case. The second smart platform that we used to develop these pattern identifiers is the fuzzy inference system. And the fuzzy inference system is basically a rule base has a rule base, and it has, of course, a normalization procedure. And the normalization function is meant to generalize the outcome of these fuzzy inference systems. Then there's the rule base, which says it's a set of if-then rules that if the input is this, the output should be that. And then there's of course, membership function for fuzzy variables. And then there's an inference engine that would aggregate all the outcomes of the rules that were fired based on the input. Again, there's some sort of testing scheme, again, to make sure that the output of this FIS system is what we expect it to do. And then in operation, you would have something like this. Again, earthquake record introduced to a structural model, time history fed to within or through the FIS, and then you would come up with a proposed abstract shape or deform shape of the system. If this is part of a controlled system, you would have, and here I'm expanding actually the fuzzy platform. So you would have a fuzzy controller and a fuzzy state identifier, and both of them would have some sort of a fuzzy dual processor, which would look like this. The fuzzy identifier would result in a shape which would be communicated to the fuzzy controller that would send signals to the MR dampers. And this is again, this is the fuzzy identifier, and this is the fuzzy controller. Now, in terms of such heuristic systems, a major concern would be reliability of these systems. And there's a lot of uncertainties and sources of uncertainties in this process. So there's the training process itself, the forcing function or the forcing earthquake, the rule base, the weights of the neural network, if you're using a neural network, the membership functions. So there's a lot of uncertainties involved. So we developed a reliability assessment framework to identify failure modes for the processor itself, or the pattern identifier itself. And using these failure modes, we can actually calculate the reliability, and then adjust the design until we reach an acceptable level of reliability. Now, this is now using what we have introduced as a pattern identifier. This is what we envision to be used in cultural heritage preservation. So we have, let's say, a minaret with sensors fixed on that minaret, and we would have, again, this is a fuzzy model. So we would have a fuzzy pattern identifier that would identify the deformed shape of this minaret at any point in time. And this shape is going to be sent to a fuzzy decision maker, which has, again, the rule base would have potential outcomes based on the shape of this minaret. If it exceeds an acceptable shape, or a certain part of it has exceeded a certain position or deformation, then it will present recommendations or sound alarms or function in that sense. So this is the FIS pattern identifier, which has, again, 3 inputs coming. I'm assuming here that we have 3 sensors. And the output would be the pattern. And this pattern is the input to the next fuzzy model, which would come up with a decision or a recommendation. And it should look like this. Input to any of these structures, set of sensors, smart identification, current state, sent to the decision maker, which might select one of these options, which is no action is required if the deformation is acceptable, immediate maintenance is required, immediate evacuation, scaffolding, other. I mean, based on the structure itself and potential states and what we accept in terms of deformation, we can make actions, recommendations, and as a result, we can take action. Thank you. This concludes my presentation, and I'm actually finished early, so I can take a couple of questions if someone would like to ask questions.
Thank you, Professor Maguid, for this nice presentation. Actually, I have seen very nice presentation and very nice talk about four things. Let me start the discussion. Professor Maguid talked about reliability analysis, fuzzy system, artificial neural networks, MR dampers, and fortunately, we have done a series of work in MR dampers, and we have currently a project. Another project is how to place MR dampers in high-rise building and contribute to the use of MR dampers for existing structures for performance assessment design or something like that. I promise by the end of this year, I will have another workshop for this topic, how to place MR dampers and dampers in general under control of tall building and high-rise building. But of course, we have to join this with our boundary element method for the building itself.
Actually, Professor Yusuf, we have done some work also in optimum allocation of MR dampers within structural systems. We have purchased a couple of small MR dampers. They are available now in our labs in the BOE, and we're planning to develop some sort of a small model so we can actually position that model on top of our small shake table and do some experimental results.
This is great. This is great. So I will ask you for two things, Professor Maguid. The first thing, to carry out a small scale building, including the slab effect, because I always talk about the inclusion of the slab effect in a building. We always test frames or something like that. We can.
I can't hear you. Your sound is breaking.
Is it clear now, Professor Maguid? Okay. What I'm saying is to have a small sample with the slab effect. A small sample with a slab effect in your test lab, then we can compare our result, our analytical result using our famous software PLPack with your results from experiment. I will ask you, this is the first thing I will ask you. The second thing, by the end of this year, I promise I will have another workshop for the tall buildings with the MR dampers. Okay? So I will ask you to participate with us.
Sure, yeah.
At the moment, I knew Professor Maguid has a very tight time because he's currently the dean of the College of Engineering.
Yes.
So we will open the discussion, but very fast. And remember, you have the feedback form. If you have any question or anything, you can write your question, and I will send it to Professor Maguid. Then we can give you a feedback. If anyone want to have a discussion or something like that, please unmute and ask your question. I can't see anybody want to participate for a question or something like that. I have one last thing, but I think Professor Shin with us, and he's a very strong guy in boundary elements. One of the things that made me notice from Professor Maguid is the use of reliability. And I believe the reliability analysis is not very famous within the context of boundary elements. I knew Sunil Saigal have done some work in reliability in boundary elements from a very long time ago, but I wanted to have some work in reliability within boundary elements. If Professor Shin with us, I would like to hear his opinion on this. I don't know he is currently with us or not. I can't see him. Maybe he's not with us currently. Maybe I will send him a question direct on email or something like this. At the moment, I would like to thank Professor Maguid. We will have something like actually less than 15 minutes for Professor Piero Francesco talk. The next talk will be control of ground vibrations through vibrating barriers. The idea of the Viba itself, who is the one who invented this idea, and we will have very nice chance to have him with us. Okay, we will give you a break for 10 minutes from now, then we will come back with Professor Piero Francesco. Thank you, everybody. Thank you, Professor Maguid.
Thank you, Professor Yusuf.